20th century opened with physics standing on what seemed like solid ground. The laws of Newton had governed the motion of planets and falling apples for centuries. Maxwell's equations explained electricity and magnetism with unmatched precision. Einstein himself, through the theory of relativity, revealed that space and time were woven together in ways no one had imagined. It seemed as though the great puzzles of the physical world were nearly solved, that the universe was a machine whose gears and levers had been laid bare for human eyes. But then came the strange, unsettling discoveries on the smallest scales of nature, discoveries that shook every assumption about how reality worked. These discoveries grew into what we call quantum mechanics, a theory that has been tested in countless experiments and never once failed, yet it remains profoundly mysterious. Even Albert Einstein, one of the greatest scientific minds in history, could never bring himself to fully accept its implications. He contributed to its foundations, but resisted its meaning. To him, the quantum world felt incomplete, as though behind its curtain of randomness, there must still be hidden rules waiting to be found. This journey through quantum mysteries begins with Einstein's uneasy relationship with the theory. It moves through the puzzles that challenged him, the paradoxes that seemed to defy logic, and the enduring enigmas that physicists still wrestle with today. The story is not one of tidy solutions, but of questions that deepen the further we explore. For every answer, new mysteries emerge. It is a story of light that behaves as both a wave and a particle, of particles entangled across the universe, of reality that shifts depending on whether it is observed. Einstein's discomfort with these ideas did not come from ignorance. He understood quantum physics better than almost anyone alive. His unease stemmed from what the theory seemed to say about reality itself, that it was not fixed, not deterministic, not governed by strict causality, but woven from probabilities and possibilities. For Einstein, who believed the universe had order and reason, this was intolerable. And so he spent much of his later life questioning, probing, and searching for a deeper explanation. The chapters that follow trace that search. They reveal the mysteries that haunted Einstein, the ones that even his genius could not solve, and how those mysteries continue to shape our understanding of the universe today. When we think of Albert Einstein, we often picture him as the architect of relativity, the man whose equations bent space and time around the speed of light. But before he revolutionized gravity, before he became the most recognized scientist on Earth, Einstein made contributions that would form the backbone of quantum mechanics. Ironically, he did so reluctantly, never fully embracing the world his ideas helped uncover. In 1905, Einstein published a paper on the photoelectric effect, a phenomenon where light striking a metal surface can knock electrons free. Classical physics could not explain why this happened. According to wave theory, the energy of light depended only on its brightness, not on its color or frequency. But experiments showed the opposite. Dim ultraviolet light could release electrons, while bright red light could not. Einstein proposed a daring solution. He suggested that light was not just a wave but came in discrete packets of energy, what we now call photons. This proposal went against everything physicists believed about light. For over a century, light had been understood as a continuous wave, just as Maxwell's equations described. Einstein's idea that it also behaved as a particle was radical. It seemed like a clever trick to solve one problem, but it opened a door to something far stranger. The idea that the fundamental building blocks of reality were not continuous, but quantized, existing in discrete amounts. For this insight, Einstein won the Nobel Prize in 1921. Yet in the years that followed, as quantum mechanics grew from scattered observations into a powerful theory, Einstein found himself increasingly at odds with the very framework he had helped launch. He respected its accuracy, but resisted its meaning. To him, The success of quantum mechanics was undeniable, but its interpretation felt incomplete, even misleading. Why this resistance? Part of it lay in Einstein's philosophical outlook. He believed deeply that nature was governed by underlying laws of order, that every effect had a cause, that the universe was rational at its core. Quantum mechanics, however, suggested a world where events could happen without definite causes, where outcomes were determined by probabilities rather than certainties. To Einstein, this was chaos dressed up as science. Despite his discomfort, Einstein could not ignore the rapid progress of quantum theory. By the 1920s, physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger were building a formal structure that described atomic behavior with unmatched precision. Quantum mechanics could predict the behavior of electrons in atoms, the structure of chemical bonds, and even the properties of materials. It worked, but it worked in a way that seemed to strip reality of solidity. Einstein often felt like an outsider in this new community. He admired the mathematical brilliance of the younger physicists, but recoiled from their willingness to accept indeterminacy as fundamental. He debated with Bohr repeatedly, sometimes in public forums that became legendary in the history of science. While Bohr argued that quantum theory revealed the limits of human knowledge, Einstein insisted that it must be pointing to something deeper, some hidden structure still undiscovered. And yet, Einstein was not simply dismissive. He contributed to many of the key discussions, raising objections that forced others to refine their arguments. His critiques often clarified what was at stake. For example, his thought experiments about measurement and observation exposed the bizarre implications of the theory, making clear just how far it strayed from common sense. Without Einstein's probing, the strangeness of quantum mechanics might not have been as fully recognized. This dual role, both father and critic, defines Einstein's place in quantum history. He was the reluctant parent of a theory he did not love, a theory that contradicted his vision of the universe, but that grew from seeds he himself had planted. His story is not one of rejection, but of wrestling, of a lifelong struggle with mysteries he could never resolve. As we move deeper into these mysteries, we see why they resisted even his genius. They are not puzzles with simple answers, but cracks in the foundation of how we think about reality. For Einstein, the struggle was not only scientific, but philosophical. It was about what it means to say something is real, whether the universe is determined or indeterminate, whether nature at its core is knowable or shrouded in probabilities. These questions haunted him to his final days, and they continue to haunt us still. At the dawn of the 20th century, physics appeared to be reaching a stage of near completion. The laws that described motion, electricity, magnetism, and gravity gave an impression of harmony. To most scientists, it seemed only a matter of filling in a few missing details before the structure of reality would be fully revealed. Yet just beneath this confidence, experiments were beginning to expose cracks in the classical picture, revealing a world that behaved in ways no one could have anticipated. Out of these cracks emerged the strange new science of quantum mechanics, a framework that would redefine what it meant to understand nature. One of the first signs that something unusual was at work came from the study of blackbody radiation, the spectrum of light emitted by objects as they are heated. Classical physics predicted that at high frequencies, the energy radiated should rise without limit. This prediction, known as the ultraviolet catastrophe, was not only absurd, but completely inconsistent with experimental results. Max Planck proposed a desperate solution in 1900. He suggested that energy itself could only be emitted or absorbed in discrete amounts, which he called quanta. Planck's idea was not intended as a revolution, but as a mathematical trick to match the data. Yet it planted the seed for a new way of thinking, one where continuity gave way to discreteness. As more phenomena were investigated, evidence piled up that the classical view could not be sustained. Atomic spectra, the distinct lines of color emitted by heated gases, could not be explained by models that treated electrons as orbiting planets around a nucleus. The old picture of atoms was elegant, but wrong. Instead, electrons appeared to jump between discrete energy levels, emitting or absorbing photons as they did so. These sudden leaps defied the smooth predictability of classical motion. Another striking revelation came from the behavior of electrons themselves. Experiments such as the double-slit test revealed that particles on the smallest scales did not behave like tiny billiard balls. When electrons were fired one by one at a pair of slits, they created an interference pattern on a screen behind them, the same pattern one would expect from waves. Each electron seemed to pass through both slits simultaneously, interfering with itself, only to arrive at the screen as a single, localized impact. If detectors were placed to observe which slit the electron passed through, the interference vanished, and the electrons behaved like particles again. This dual nature of matter was unlike anything in classical physics. The growing strangeness was not limited to light and electrons. Protons, neutrons, and even entire atoms displayed similar behaviors when probed at the quantum scale. The very building blocks of matter seemed to exist in a realm where intuition failed. Position and momentum could not both be known with complete certainty, as Werner Heisenberg formulated in his uncertainty principle. Instead of a universe where every detail could, in principle, be measured and predicted, quantum mechanics presented a reality where fundamental limits were built into nature itself. The mathematics developed to handle these discoveries only deepened the mystery. Erwin Schrödinger's wave equation described how quantum systems evolved over time, predicting probabilities rather than certainties. Max Born proposed that the wave function itself represented the likelihood of finding a particle in a given place. Suddenly, the bedrock of physical science shifted from deterministic laws to statistical ones. The behavior of atoms, electrons, and photons could be calculated with incredible accuracy, but the outcome of any individual event was left to chance. For scientists raised on the principles of Newton and Maxwell, this probabilistic universe was unsettling. In classical mechanics, if one knew the positions and velocities of all particles, the future could be predicted with absolute precision. Quantum mechanics shattered that confidence. Even with perfect knowledge of the wave function, only probabilities could be given. Nature, it seemed, had an element of unpredictability at its core. Yet what disturbed physicists most was not only the randomness, but the role of measurement itself. In the quantum framework, the act of observing a system did not merely reveal a pre-existing reality. Instead, measurement appeared to affect the system, collapsing the wave of possibilities into a single outcome. Before observation, an electron could be thought of as existing in many states at once, spread out across space. The moment it was measured, it appeared in one definite location. This connection between observation and reality raised profound questions about whether the universe existed in a definite state independent of our measurements. The early pioneers of quantum theory responded to these challenges in different ways. Niels Bohr developed the principle of complementarity, suggesting that quantum entities could display both wave-like and particle-like properties, but never both at once. He argued that the apparent contradictions arose because human language and classical concepts were inadequate to fully describe the quantum domain. According to Bohr, quantum mechanics was not about depicting reality as it truly is, but about predicting the outcomes of experiments. Others, like Heisenberg, embraced the uncertainty principle as a fundamental truth of nature, not a limitation of human knowledge. The universe, they argued, was not clockwork but probabilistic. Still others, including Schrödinger himself, were troubled by the implications. His famous thought experiment of the cat in a box, simultaneously alive and dead until observed, was meant as a critique of the prevailing interpretation. highlighting its strangeness when extended beyond the atomic scale. These early debates revealed how far quantum mechanics had moved from the comfortable world of classical physics. In the classical view, objects had definite properties regardless of whether anyone observed them. In the quantum view, properties seemed to emerge only when measured. Space and time themselves retained their familiar roles, but the entities that inhabited them no longer followed the rules of common sense. Despite the philosophical unease, the practical success of quantum mechanics could not be denied. It explained the stability of atoms, the behavior of semiconductors, and the interactions of light and matter. It gave rise to technologies such as lasers, transistors, and eventually the digital revolution. Every prediction confirmed by experiments strengthened the theory, even as its interpretation remained opaque. The birth of quantum mechanics thus represented a profound rupture in human understanding. It was not merely a new chapter in physics, but a reimagining of what science itself could say about reality. Instead of certainty, it offered probabilities. Instead of a clear picture of what particles were doing, it offered wave functions that described possibilities. It was, in the words of many who first encountered it, weird, unsettling, and deeply counterintuitive. What made this shift especially remarkable was how quickly it transformed the scientific landscape. Within a few decades, the old certainties of Newtonian determinism had been replaced by a framework that accepted uncertainty as fundamental. Physicists adapted to the new rules, but the unease never fully disappeared. Even those who worked daily with quantum mechanics often admitted they did not truly understand it. The mysteries that emerged in this period would haunt generations of scientists. They revealed a universe stranger than anyone expected, a universe where reality itself seemed to depend on the act of observation. This was the landscape that Einstein found himself confronting, a landscape shaped partly by his own discoveries, yet alien to his philosophical convictions. Quantum mechanics had been born, and with it came the first glimpses of puzzles that no one, not even Einstein, could resolve. The rapid rise of quantum mechanics during the 1920s captivated most of the physics community, but for Albert Einstein, it created an inner conflict that grew deeper with every passing year. He had no doubt about the accuracy of the equations or the reliability of the predictions. The new theory worked astonishingly well in practice, producing results that experiments confirmed again and again. Yet Einstein refused to believe that the randomness built into the theory represented a true description of nature. To him, it was not a reflection of reality, but a sign that something essential was missing. The phrase that became attached to his resistance, "God does not play dice with the universe," was more than a clever turn of words. It condensed his entire philosophical stance toward physics. Einstein believed the universe must be governed by order, structure, and causality. Every effect, no matter how small, must arise from a cause. Randomness, in his view, was not a fundamental aspect of nature, but an admission of ignorance. If a die lands showing 3, that result is not due to chance but to the precise forces acting on it. The angle of the throw, the speed of the hand, the texture of the table, and countless other details. The outcome looks random because those details are hidden, not because they do not exist. Einstein applied the same reasoning to quantum mechanics. If an atom emits a photon in one direction rather than another, the reason might be beyond current knowledge, but it must be there. This conviction put Einstein at odds with colleagues who had embraced the indeterministic character of the quantum world. For them, the probabilistic interpretation was not a flaw, but a feature. Niels Bohr argued that the uncertainty was built into nature itself, that particles did not have definite properties until they were observed. To Bohr, quantum mechanics revealed the limits of what could be known. To Einstein, this sounded like surrender. He was unwilling to believe that nature itself was fundamentally unknowable. Einstein's resistance was not simply a matter of stubbornness. He had spent his career uncovering hidden order beneath appearances. His special theory of relativity showed that time and space, once thought separate, were aspects of a unified continuum. His general theory of relativity revealed that gravity, which had seemed like an invisible force, was the curvature of space-time itself. Again and again, Einstein had shown that behind the apparent chaos of phenomena there was deep structure. To him, it was only natural to assume that the apparent indeterminacy of quantum events also hid a deeper law. This belief motivated Einstein's debates with Bohr and the Copenhagen school. Their exchanges became legendary, not only for their intellectual intensity, but for the way they embodied two competing visions of reality. Bohr insisted that physics was not about describing reality in itself, but about predicting the outcomes of experiments. Einstein countered that physics without a real underlying world was incomplete. These were not mere disagreements about equations, but about the very purpose of science. In his objections, Einstein often used thought experiments to expose what he saw as contradictions in the quantum framework. One famous example involved imagining a box filled with radiation, fitted with a shutter and a scale to measure its weight. According to Einstein, by timing the release of a single photon and measuring the change in weight of the box, one could know both the energy of the photon and the time of its emission with arbitrary precision. This, he argued, violated the uncertainty principle. Bohr responded by invoking general relativity, pointing out that the act of measuring weight depended on gravitational effects that reintroduced uncertainty. For Bohr, the uncertainty principle remained intact. These duels, while technical, carried immense philosophical weight. The heart of Einstein's objection lay in his refusal to abandon determinism. He could not accept a universe where outcomes were dictated purely by chance. He suspected that quantum mechanics was a provisional theory, one that worked but was incomplete, like a shadow of a deeper reality. He spoke of hidden variables, unknown factors that would restore causality to physics once they were discovered. To him, the wave function was not a complete description, but a statistical summary of underlying processes. Einstein's phrase about dice was not meant literally. He did not believe in a personal deity intervening in the workings of nature. For him, God represented the rational order of the cosmos, the mathematical elegance that could be uncovered by the human mind. To say that God does not play dice was to insist that the universe is governed by laws, not by randomness. The mystery of quantum mechanics was therefore not that it showed randomness, but that it revealed the limits of current understanding. This conviction shaped the rest of Einstein's career, while others pushed quantum mechanics forward, building the foundations of modern atomic and particle physics. Einstein turned his attention elsewhere. He sought unified theories that might reconcile relativity and electromagnetism, hoping that such a deeper framework would also reveal the missing structure behind quantum phenomena. Though he did not succeed, his refusal to accept randomness as fundamental kept the debate alive and forced others to sharpen their interpretations. Einstein's resistance to quantum indeterminacy was not a rejection of progress, but a defense of a vision of science he had always held. For him, science was a path toward uncovering reality, not merely predicting observations. His discomfort with probability was therefore philosophical as much as scientific. It was about whether the universe could truly be known, whether nature's secrets were discoverable or forever hidden behind a veil of chance. The debates between Einstein and Bohr illuminated this tension. On one side was the insistence that physics should describe reality as it is. On the other was the pragmatic acceptance that physics might only describe what can be measured. Einstein's voice carried the weight of his earlier triumphs. Yet the new generation of physicists embraced the probabilistic view, guided by the undeniable success of the theory in practice. As the years passed, Einstein's dice metaphor became a symbol of resistance against quantum indeterminacy. It captured his refusal to yield to a vision of the universe that lacked causality. Even as quantum mechanics became the foundation of modern physics, Einstein continued to believe that something essential was missing. The dice, in his view, were only an illusion, a product of ignorance rather than reality. The legacy of his objection lives on. While most physicists accept the probabilistic nature of quantum mechanics, questions remain about whether hidden structures might still exist. The search for deeper laws, for hidden order behind apparent randomness, continues in efforts to unify physics at its most fundamental levels. Einstein's famous words, meant as a protest, have become a reminder of the tension between accepting nature as it appears and striving to uncover what lies beneath. For centuries, light was a mystery that fascinated philosophers and scientists alike. Was it made of particles, like streams of tiny projectiles racing through space? Or was it a continuous wave spreading across the cosmos like ripples on water? This question defined much of physics in the 18th and 19th centuries, and by the time of Einstein's youth, the consensus leaned heavily toward the wave description. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single elegant framework, showing that light was an electromagnetic wave. The triumph of Maxwell's theory was so complete that many physicists believed the question was settled forever. Yet beneath this apparent certainty, light held a paradox, one that would later force even Einstein to confront contradictions at the heart of reality. The paradox began to emerge with experiments that simply could not be reconciled with a purely wave-based picture. One of the most famous was Thomas Young's double-slit experiment in the early 1800s. When light was shone through two closely spaced openings, it created an interference pattern on a screen behind them. Bands of bright and dark fringes that could only be explained if light behaved as a wave. If light were made of particles, one would expect two bright spots corresponding to the two slits. Instead, the overlapping waves reinforced each other in some places and cancelled in others, producing the distinctive interference pattern. To generations of physicists, this seemed to prove once and for all that light was a wave. But then came evidence pointing in the opposite direction. At the end of the 19th century, the photoelectric effect showed that light striking a metal surface could knock electrons free, but only if the light was above a certain frequency. No matter how bright the light, if its frequency was too low, no electrons were ejected. On the other hand, even a faint beam of high-frequency light could liberate electrons with measurable energy. The wave theory could not explain this. It was Einstein who solved the puzzle in 1905 by proposing that light came in discrete packets, quanta of energy, later called photons. Each photon carried energy proportional to its frequency, explaining why higher frequency light could dislodge electrons while lower frequency light could not. This discovery earned Einstein the Nobel Prize and established the foundation of quantum theory. Yet it left him unsettled. For here was the paradox. In some experiments, light behaved undeniably as a wave, while in others it behaved as a particle. It was not one or the other, but somehow both, depending on how it was observed. This duality was unlike anything in classical physics, which relied on clear categories. Waves and particles had always been distinct. Waves spread out, interfered, and overlapped. Particles were localized, discrete, and countable. Light seemed to belong to both categories and to neither fully. As experiments grew more precise, the duality only deepened. Single photons sent through a double slit still produced an interference pattern over time, as though each photon traveled through both slits at once and interfered with itself. Yet when measured at the slits, photons were detected as localized impacts, not spread out waves. This raised a profound question. What was light doing between the source and the screen? Did it travel as a wave of possibilities that collapsed into a particle upon detection? Or did it exist in some other form beyond human categories? The paradox of wave-particle duality did not stop with light. Matter itself once thought to be composed of solid, indivisible particles, revealed the same dual nature. Electrons, protons, even entire atoms exhibited interference patterns when passed through slits or diffracting gratings. The implication was staggering. Everything in the universe, from the smallest photon to the largest molecule, had both particle-like and wave-like properties. What separated them was not their nature, but the scale at which they were observed. For Einstein, the wave-particle paradox was one of the most troubling features of quantum mechanics. While he had introduced the idea of light quanta, he never accepted the interpretation that photons somehow existed in superposed states until measured. To him, the photon was either a particle or it was not. The idea that reality could shift based on observation felt incomplete. He argued repeatedly that the duality must be pointing to a deeper theory, one in which photons had definite states at all times, whether or not they were being observed. Despite his protests, the wave-particle paradox became a cornerstone of quantum mechanics. Niels Bohr framed it in terms of complementarity. Light could be described as a wave or as a particle, depending on the experimental setup, but never both at once. These descriptions were not contradictory, but complementary. Two aspects of the same underlying reality that could never be fully grasped at once. This view was unsatisfying to Einstein, who wanted a consistent description independent of the observer. The paradox raised deeper philosophical questions. If light and matter could be both waves and particles, what did that say about the categories we use to describe reality? Were waves and particles simply human constructs, inadequate for describing the quantum world? Was the universe itself beyond any simple picture? These questions challenged not only physics, but also the very way humans conceive of knowledge. Practical applications of wave-particle duality soon emerged, even as its meaning remained elusive. Quantum mechanics could predict the behavior of electrons in atoms, the emission of photons from excited states, and the scattering of particles in collisions. The mathematics was powerful and reliable. Engineers built devices such as transistors, lasers, and semiconductors based on these principles, revolutionizing technology. Yet the underlying paradox remained unresolved. Einstein continued to challenge the notion that light and matter existed in superposed states. He believed that a hidden framework, perhaps undiscovered variables, must explain the duality in a deterministic way. Though he was in the minority, his objections kept the conversation alive, reminding others that success in prediction did not necessarily mean success in understanding. The paradox of light was thus not simply a scientific puzzle, but a philosophical rift. It revealed a universe where categories blurred, where observation determined behavior, and where the most fundamental phenomena refused to fit human intuition. Light, once thought to be the most familiar of natural phenomena, had become a symbol of mystery. It illuminated not only the physical world, but the limits of human comprehension. For Einstein, the struggle with this paradox never ended. He had opened the door to the quantum description of light, but could not accept the world it revealed. The duality stood as a constant reminder that even the greatest scientific minds could be unsettled by the mysteries of nature, mysteries that refused to yield to classical logic. Light was no longer just illumination. It was a riddle written into the fabric of reality itself. By the mid-1930s, Einstein's frustration with the strange implications of quantum mechanics had reached its peak. He had already argued against the idea of randomness in the heart of nature and against the dual identity of light. But there was one thought experiment, developed in collaboration with Boris Podolsky and Nathan Rosen, that crystallized his objections more sharply than anything before. It came to be known as the Einstein-Podolsky-Rosen paradox, or simply the EPR paradox. The central question was deceptively simple. Was quantum mechanics a complete description of reality, or was it merely a temporary framework that would eventually be replaced by something deeper? To Einstein, the answer was obvious. Quantum mechanics worked, But it could not be the whole story. It gave powerful predictions, but it left no room for an underlying objective reality existing independently of measurement. For a man who had spent his career uncovering the order behind the universe, this was deeply unsatisfying. The EPR paper, published in 1935, set out to demonstrate that quantum mechanics was incomplete. Einstein and his colleagues focused on one of the most puzzling consequences of the theory: entanglement. According to quantum mechanics, two particles that had interacted could become linked in such a way that their properties were no longer independent. Instead, they formed a single unified system. No matter how far apart they traveled, measure the spin or momentum of one particle, and the other's state would be instantly determined, even if it were across the universe. This was not just strange, it seemed impossible. Einstein famously called it spooky action at a distance. To him, this kind of instantaneous connection violated one of the pillars of physics, that no signal or influence could travel faster than the speed of light. Relativity had shown that nothing outran light. Not information, not energy, not cause and effect. Yet here was quantum mechanics suggesting otherwise. The thought experiment went like this. Imagine two particles created in such a way that their total momentum was conserved. If one particle moved left, the other had to move right with equal momentum. If one particle was measured to spin up, the other had to spin down. Quantum mechanics described the pair as a single wave function, a mathematical object containing all possible outcomes. Only when one particle was measured did the wave function collapse, instantly fixing the outcome of the other. Einstein, Podolsky, and Rosen argued that this implied one of two things. Either information was traveling faster than light between the particles, which contradicted relativity, or the particles had hidden properties that predetermined their outcomes all along. The second option, they believed, was the only sensible explanation. The apparent randomness of quantum mechanics was simply a reflection of ignorance about these hidden variables. Once those hidden details were uncovered, the paradox would vanish, and physics would return to a deterministic framework. The EPR paradox was not a dismissal of quantum mechanics, but a challenge to its claim of completeness. Einstein acknowledged that the mathematics worked, but he insisted that it was provisional, a tool that concealed deeper truths yet to be discovered. For him, the universe could not be based on instantaneous influences stretching across space. Reality had to be local. Causes must precede effects, and nothing should leap from one place to another without crossing the intervening space. Niels Bohr, the great defender of the Copenhagen interpretation, responded quickly to the EPR paper. To Bohr, Einstein's insistence on hidden variables and local realism was misguided. He argued that entanglement did not represent faster-than-light communication, but rather a fundamental wholeness of the quantum world. The properties of particles were not defined until measured, and the act of measurement was inseparable from reality itself. The strange correlations were not signals traveling through space, but expressions of an underlying unity that transcended classical notions of locality. The debate between Einstein and Bohr became one of the most famous intellectual rivalries in the history of science. Einstein, with his insistence on order, clarity, and determinism, could not accept a universe built on probabilities and non-local connections. Bohr, with his embrace of paradox and complementarity, believed that Einstein was clinging to outdated concepts that had no place in the quantum world. Their exchanges were sharp, sometimes heated, but always rooted in a shared respect for the pursuit of truth. For decades, the EPR paradox remained a thought experiment. The technology to test its predictions did not exist, but its implications lingered in the minds of physicists. Was quantum mechanics truly describing reality, or was it only a shadow of a deeper, hidden structure? The paradox forced physicists to confront uncomfortable questions about the nature of information, causality, and the limits of human understanding. It wasn't until the 1960s that physicist John Bell formulated a way to test the competing ideas. Bell's theorem showed that if hidden variables existed, they would impose strict statistical limits on the correlations between entangled particles. Quantum mechanics, by contrast, predicted stronger correlations. Experiments inspired by Bell's work in the following decades consistently confirmed the predictions of quantum mechanics. Entanglement was real, and the universe was non-local in a way that defied Einstein's vision. Yet even with these experimental results, the philosophical unease remained. If particles could influence each other across space without any signal passing between them, what did that say about the nature of reality itself? Were space and time truly the fundamental framework of the universe? Or were they emergent properties of something deeper? The EPR paradox did not simply challenge Einstein's beliefs. It opened a door to questions that science is still grappling with today. Einstein never accepted entanglement as a fundamental feature of reality. To him, it was evidence that quantum mechanics was incomplete. He died believing that the universe had a more coherent structure waiting to be revealed, one that preserved locality and determinism. The EPR paradox thus stands not only as a scientific milestone, but as a window into the mind of a man who refused to accept that reality was governed by chance and spooky connections. In the decades since, entanglement has become more than a philosophical puzzle. It is now the foundation of quantum information science, powering advances in quantum computing, quantum cryptography, and teleportation protocols. What Einstein once rejected as unthinkable has become one of the most important tools in modern physics. The paradox remains, but its consequences have reshaped our technological world. The EPR paper, written in the language of challenge and skepticism, continues to echo through physics. It reminds us that even the greatest theories are not beyond question, and that progress often comes from those unwilling to accept easy answers. Einstein may have resisted the conclusions of quantum mechanics, but by raising his objections, he pushed the field to deeper insights. Entanglement is one of the strangest and most unsettling features of the quantum world. It describes a situation in which two or more particles become so deeply connected that the state of one cannot be described without reference to the other, no matter how far apart they travel. This isn't just a matter of correlation, like two clocks being set to the same time. Instead, it is a profound unity, where measurement of one particle's properties instantaneously fixes the properties of its partner. To Einstein, this idea was unacceptable. To modern physics, it has become one of the most fundamental truths about reality. When two particles interact in the quantum realm, their wave functions become intertwined. Imagine an electron and a photon colliding in a way that conserves both energy and spin. After this interaction, their individual identities are no longer separate. The mathematics shows that the system must be described by a single wave function, a superposition of possibilities that binds them together. Measure the spin of the electron, and you immediately know the spin of the photon. It does not matter if the particles are across the lab or across the galaxy. Their properties remain linked as though they are still part of one whole. To see why this was so troubling for Einstein, it helps to remember his belief in locality. Locality means that objects are influenced only by their immediate surroundings. A planet feels the gravitational pull of the sun because of the curvature of space-time. But no planet can leap into motion without something acting upon it. This principle underlies not only relativity but much of classical science. Entanglement seems to break this rule. It suggests that particles can influence each other without crossing the space between them, as if distance simply doesn't matter. Physicists in the 1930s and 1940s debated whether entanglement was a genuine feature of the universe or simply a quirk of the mathematics. Some thought of it as a bookkeeping device, a way to keep track of correlations without assuming anything physically mysterious was happening. Others took it at face value, arguing that the universe was stranger than anyone had imagined. Einstein placed himself firmly in the first camp. For him, entanglement was a sign that quantum mechanics was incomplete, a clue that hidden variables must exist beneath the surface. But as the decades passed, evidence accumulated that entanglement was more than an artifact. Careful experiments showed that entangled particles produced correlations stronger than any classical system could explain. When physicists measured pairs of photons or electrons, the outcomes were linked in ways that violated inequalities derived from classical assumptions. This was not mere coincidence. The results pointed to a reality in which entanglement was not optional but unavoidable. The implications of entanglement reach far beyond physics. It forces a reconsideration of the very nature of separateness. In classical thought, objects are distinct entities, each with its own independent state. In the quantum world, that independence dissolves. Objects that have interacted once remain part of a shared state, no matter how far they travel apart. It is as if the universe itself is woven together. A tapestry in which threads connect distant regions in invisible but undeniable ways. This interconnectedness has inspired more than scientific curiosity. Philosophers and even spiritual traditions have pointed to entanglement as evidence that reality may be unified at a level deeper than everyday perception. While physicists avoid such interpretations in their technical work, the metaphor of a web of reality has become a powerful way of expressing what entanglement suggests. Separateness is an illusion. Einstein, however, never accepted this. His vision of the cosmos was one of clarity and structure. He believed in a universe where causes and effects unfolded according to laws that were consistent everywhere, independent of observers. Entanglement seemed to mock this view, replacing it with a picture where boundaries blurred and certainty dissolved. To him, it was not a revelation, but a puzzle, one that indicated quantum mechanics was pointing in the wrong direction. And yet, entanglement is now the basis of technologies that Einstein could never have imagined. Quantum cryptography uses it to create secure communication channels, exploiting the fact that any attempt to tamper with entangled particles destroys their correlation. Quantum computers rely on entanglement to link qubits, giving them computational power far beyond classical machines. What Einstein once dismissed as spooky action at a distance is now being harnessed as a practical resource. Even more remarkable is the way entanglement has shaped new theories about space and time themselves. Some physicists now argue that the very fabric of space may be built from entanglement, that the geometry of the universe arises from quantum correlations between particles. If true, this would mean that what Einstein saw as a flaw in quantum mechanics may in fact hold the key to unifying relativity and quantum theory. Entanglement, then, is not just a curiosity of the quantum world. It is a challenge to the way we understand existence. It undermines the classical picture of separateness, hints at deeper connections, and suggests that the universe is more holistic than mechanistic. Einstein resisted this vision, but the evidence continues to grow that entanglement is fundamental. The story of entanglement is also the story of humility in science. It reminds us that the universe does not conform to human expectations. Even the greatest minds can be unsettled by truths that refuse to fit established frameworks. Einstein's rejection of entanglement shows how deeply ingrained locality and determinism were in his worldview, and how radical quantum mechanics truly is. Today, entanglement is no longer viewed as a paradox, but as a cornerstone. Its contradictions with Einstein's vision are not weaknesses but windows into a deeper reality. The web of connections it reveals is reshaping both theory and technology, binding the smallest particles into patterns that span the cosmos. What began as a challenge to the completeness of quantum mechanics has become one of the strongest confirmations of its strange but undeniable power. Among the many puzzles that arose from quantum mechanics, few captured the tension between logic and paradox as vividly as Schrödinger's cat. Conceived in 1935 by Austrian physicist Erwin Schrödinger, the thought experiment was meant as a critique, a way of exposing the absurd consequences of taking the Copenhagen interpretation of quantum mechanics too literally. Yet instead of discrediting the theory, the cat became one of its most enduring symbols. For Einstein, it reinforced his growing unease with the role of observation in shaping reality. The thought experiment was simple in outline, but devastating in implication. Imagine a sealed box containing a living cat, a small vial of poison, a Geiger counter, and a tiny amount of radioactive material. The radioactive material has a 50% chance of decaying within an hour. If it decays, the counter detects it, triggers a mechanism, and releases the poison, killing the cat. If it does not decay, the cat survives. According to the mathematics of quantum mechanics, until the box is opened and the system is observed, the radioactive atom exists in a superposition of decayed and undecayed states. Consequently, the cat is in a superposition as well, both alive and dead at the same time. To Schrödinger, this was absurd. He never intended it as a literal description of reality, but as a way of showing the strangeness of applying quantum rules to everyday objects. How could a cat be both alive and dead? Surely, he argued, there must be a boundary between the microscopic world of atoms, where superpositions could exist, and the macroscopic world of ordinary experience, where outcomes are definite. His point was not to embrace the paradox, but to highlight its absurdity. The cat, however, took on a life of its own. To the defenders of the Copenhagen interpretation, the experiment illustrated precisely the role of observation in collapsing possibilities into reality. The cat was not both alive and dead in any literal sense, they argued. Rather, the quantum description reflected our knowledge of the system. Once the box was opened, the wave function collapsed into one outcome or the other, and the paradox resolved. For Einstein, this reasoning was deeply unsatisfying. He believed that physical systems had definite states whether or not they were observed. The cat was alive or dead before the box was opened, not both. To suggest otherwise was to abandon realism, the belief that reality exists independently of observers. He saw the cat paradox as a demonstration not of quantum mechanics' completeness, but of its flaws. To him, it revealed that the theory could not be the final word on nature. The problem of observation lay at the heart of Einstein's objections. In classical physics, observation was passive. A thermometer did not create the temperature it measured, and a telescope did not determine the position of a star. Measurement revealed properties that already existed. Quantum mechanics turned this notion on its head. According to its formalism, properties like position, momentum, and spin did not exist in definite states until measured. The act of observation played an active role, collapsing a superposition into a single outcome. This idea troubled Einstein to no end. He often mocked the suggestion that the moon existed only when someone looked at it. For him, the universe was objective and independent, not subject to the whims of measurement. The idea that observation created reality was, in his view, a step backward into mysticism, not progress toward understanding. Schrödinger himself shared some of Einstein's concerns. He too was skeptical of the idea that quantum superpositions extended into the macroscopic world. Yet, unlike Einstein, who spent decades opposing the theory, Schrödinger grew more ambivalent, exploring the implications of superposition with curiosity rather than outright rejection. The cat paradox, intended as a critique, became a springboard for discussions about the nature of reality, probability, and information. The observer problem did not end with Schrödinger's cat. It grew into one of the central puzzles of quantum theory. What exactly counts as an observation? Is it the interaction with a measuring device, the involvement of a conscious observer, or something deeper? Different interpretations of quantum mechanics offered different answers. Bohr emphasized the role of classical measuring apparatus. Others suggested that consciousness itself played a role, collapsing the wave function. Still others propose that all outcomes occur in parallel, branching universes that render the paradox moot. Einstein rejected these explanations as unsatisfying or unscientific. To him, they were evasions rather than solutions. He wanted a theory that restored objectivity, that described particles and systems as they truly were, not merely as they appeared when observed. His resistance to the observer-centric view was not mere stubbornness, but a reflection of his commitment to realism. He could not accept that human observation had such a privileged place in the fabric of the universe. The cat paradox remains powerful because it dramatizes the problem in concrete terms. It takes the abstract mathematics of quantum superposition and translates it into an image everyone can understand. A cat suspended between life and death until the box is opened. The absurdity of the image forces us to confront the deeper absurdity of the underlying theory, whether one accepts it as a real possibility or rejects it as nonsense depends on one's philosophical stance toward reality itself. Modern physics has made progress in addressing the problem of observation, though not in the way Einstein might have hoped. The development of decoherence theory, for instance, shows how interactions with the environment effectively destroy superpositions in macroscopic systems, making them appear classical. According to this view, the cat is not truly both alive and dead, because interactions with the environment force one outcome to emerge long before anyone opens the box. Yet even decoherence does not fully resolve the philosophical puzzle. It explains why superpositions are not observed in large systems, but does not settle whether reality itself is objective or observer-dependent. For Einstein, Schrödinger's cat confirmed that quantum mechanics was incomplete. It dramatized his conviction that the theory's reliance on observation was untenable. He believed that a deeper, hidden structure must exist, one in which reality had definite states independent of measurement. The cat was never both alive and dead, only waiting for humans to discover which. The enduring power of the cat paradox lies in its ability to crystallize the problem of observation in a way no equation could. It embodies the tension between the quantum and classical worlds, between probabilities and definiteness, between realism and observer dependence. For Einstein, it was yet another reason to doubt that quantum mechanics could ever serve as the final description of nature. For others, it became a symbol of the quantum revolution itself, a reminder that the universe defies common sense and forces us to reconsider the foundations of knowledge. For Einstein, the refusal to accept the indeterminacy of quantum mechanics was not a matter of stubborn pride, but a matter of principle. He believed deeply that the world was governed by order, not chance. The universe, in his view, operated with laws so precise that the motion of planets, the curvature of light near stars, and the ticking of atomic clocks could all be traced back to unshakable rules. Quantum mechanics, with its insistence that outcomes could only be predicted as probabilities, felt incomplete. It was not wrong in its predictions, but it seemed to leave out something essential: the deeper layer of reality that determined those probabilities in the first place. Einstein called this missing foundation the hidden variables. These were the unseen elements of reality that, if uncovered, would restore determinism to physics. In this vision, particles had definite positions and momenta, even if we lacked the tools to measure them precisely. The apparent randomness of quantum outcomes, he believed, was simply the reflection of ignorance. Just as the roll of dice feels random until one recognizes the exact conditions of the throw, quantum randomness would vanish once the hidden variables were revealed. The appeal of this view was obvious. It preserved the idea that the universe is not ruled by chance, but by underlying order. It saved the notion of realism, the idea that objects exist in definite states whether observed or not. It also aligned perfectly with Einstein's lifelong commitment to finding unity and coherence in the natural world. To him, Physics was not about surrendering to probabilities, but about uncovering the laws that make those probabilities unnecessary. The debate over hidden variables sharpened in the 1930s and 1940s, especially after the publication of the Einstein-Podolsky-Rosen paper. In it, Einstein and his collaborators argued that if quantum mechanics were complete, it would imply spooky action at a distance. The alternative they suggested was that quantum mechanics was an incomplete description of reality, one that could eventually be supplemented by hidden variables. Bohr countered that the theory was complete as it stood, that quantum states did not represent hidden truths, but rather the full extent of what could be known. For Einstein, this was not convincing. He rejected the idea that physics should abandon realism or determinism. He saw hidden variables not as speculation, but as a necessity. Without them, physics would lose its foundation in causality. In private conversations and public debates, he pressed this point with unwavering consistency. Even as he worked on other problems, from unified field theory to cosmology, the conviction lingered. Quantum mechanics must be incomplete. Over time, the hidden variables idea took on many forms. Some physicists sought to construct explicit models in which particles carried definite properties that were merely hidden from measurement. Others tried to reconcile the mathematical success of quantum mechanics with the intuitive clarity of deterministic systems. None of these attempts gained wide acceptance during Einstein's lifetime, but they kept alive the hope that quantum indeterminacy was only temporary, a reflection of incomplete knowledge rather than fundamental randomness. The hidden variables debate also revealed a deeper philosophical divide. On one side were those, like Bohr and Heisenberg, who embraced the idea that uncertainty was built into nature itself. On the other side were those like Einstein, who insisted that uncertainty was only a reflection of human limitation. This divide was not merely technical, but existential. It touched on the very meaning of science. Was it the description of what can be known, or the uncovering of what exists independently of knowledge? Einstein often illustrated his stance with analogies. A gambler might think the outcome of a coin toss is uncertain, but in reality, the motion of the coin is determined by physical laws. If one knew every detail of the coin's position, velocity, and rotation, the outcome could be predicted with certainty. In the same way, quantum mechanics seemed to him like a gambler's perspective, useful for predictions, but ultimately shallow in its refusal to acknowledge hidden causes. This conviction shaped Einstein's relationship with the physics community. While many physicists were content to use quantum mechanics as a practical tool, Einstein treated it as a provisional theory. He acknowledged its accuracy but never its completeness. In letters and lectures, he returned again and again to the need for hidden variables, even as younger physicists dismissed the idea as outdated. He was not clinging to the past but pressing for a deeper future. The persistence of the hidden variables debate is a testament to the power of Einstein's vision. Decades after his death, the question of whether quantum mechanics is truly complete remains alive. Experimental tests have probed the limits of hidden variable theories, challenging and refining them. Some interpretations of quantum mechanics incorporate hidden elements in sophisticated ways, while others reject them outright. What unites all of these discussions is the recognition that Einstein's dissatisfaction forced the field to sharpen its arguments, to confront the philosophical stakes, and to explore possibilities that might otherwise have been ignored. The heart of the matter was not simply technical, but philosophical. Could the universe truly be governed by chance at its most fundamental level? For Einstein, the answer was no. His commitment to hidden variables was an extension of his belief in a rational cosmos, one where order prevails beneath the surface of apparent chaos. Even if the details of those hidden variables were beyond reach, their existence, he believed, was certain. This conviction placed him at odds with many of his contemporaries. But it also ensured that his legacy would not be confined to relativity alone. By challenging quantum mechanics, he opened the door to questions that still shape the field. The hidden variables debate remains a central part of the story of quantum theory, a reminder that even the most successful equations may not capture the whole of reality. Einstein did not resolve the paradox, nor did he provide a definitive hidden variables theory. What he offered instead was a challenge: to seek deeper order, to resist complacency, and to remember that science is not only about what works but about what is true. That challenge continues to echo through physics, as researchers push beyond probabilities in search of the structures that might lie beneath. For decades after Einstein, Podolsky, and Rosen put forward their paradox, the question of whether quantum mechanics was complete remained a matter of philosophical speculation rather than experimental fact. Physicists continued to rely on the quantum framework because it worked, producing results that were unmatched in accuracy. Yet beneath the surface, the unease lingered. Was the apparent randomness of quantum events fundamental? Or was it simply masking a hidden layer of deterministic rules? This unresolved tension shaped physics throughout the mid-20th century, waiting for someone to find a way to put the matter to the test. That someone was John Bell, a quiet but brilliant physicist from Northern Ireland, who, in the 1960s, accomplished what Einstein could not. Instead of treating the debate as a matter of philosophy, Bell translated it into the language of mathematics and experiment. He asked a deceptively simple question: if hidden variables existed, what measurable differences would they produce compared to the predictions of standard quantum mechanics? Could one design an experiment that would distinguish between Einstein's vision of local realism and the non-local strangeness embraced by Bohr? Local realism was the principle Einstein defended until his last days. It combined two ideas: locality, meaning no influence can travel faster than the speed of light, and realism, meaning that objects possess definite properties independent of observation. Hidden variables, if they existed, would preserve both of these principles. But Bell suspected that this assumption could be tested in a concrete way. What he derived is now known as Bell's theorem. At its heart was an inequality, a mathematical boundary that any local hidden variable theory must obey. If measurements of entangled particles ever violated this inequality, it would mean that local realism could not explain the data. The outcome would be unavoidable. Either reality was non-local, allowing influences to leap across space instantaneously, or particles did not possess definite properties until they were measured. Both possibilities defied Einstein's vision of a rational, deterministic cosmos. The beauty of Bell's work lay in its clarity. He showed that the abstract debates between Einstein and Bohr could be settled not by philosophical argument, but by experimental evidence. Physics, once again, would be determined by what nature itself revealed, not by what theorists preferred. The stage was set for one of the most profound shifts in scientific history. When experiments began to test Bell's inequality in the 1970s and 1980s, the results were staggering. Time after time, quantum mechanics emerged victorious. Entangled particles, when measured in carefully controlled setups, violated Bell's inequality just as quantum theory predicted. The hidden variable explanations Einstein had hoped for fell away, replaced by the stark reality that the universe did not conform to local realism. The implications were earth-shaking. If Bell's theorem was right, then either information traveled instantaneously between entangled particles, or reality itself had no definite structure until observed. Both possibilities seemed impossible, yet experiments left no doubt. The choice was not between comfort and strangeness, but between different kinds of strangeness. Physicists around the world struggled to make sense of these findings. Some accepted non-locality, conceding that entanglement meant the universe was woven together in ways that transcended space and time. Others leaned toward interpretations that abandoned realism, insisting that particles had no definite states until measured. Either way, the clear, deterministic universe Einstein fought to preserve was shattered. John Bell himself remained modest about his achievement. He recognized that his theorem did not tell physicists which interpretation of quantum mechanics was correct. What it did was more radical. It ruled out entire categories of explanations that clung to the comforting ideas of locality and realism. By narrowing the field, Bell forced the physics community to confront the full depth of quantum weirdness. The experimental confirmation of Bell's work reshaped physics in ways Einstein might never have anticipated. Quantum entanglement, once dismissed as a paradox, became central to new technologies such as quantum cryptography and quantum computing. What Einstein had dismissed as spooky action at a distance became a resource to be harnessed. The same phenomenon that troubled him now promised to revolutionize communication, computation, and security. And yet, the victory of quantum mechanics over hidden variables was not absolute in spirit. Even as Bell's theorem ruled out local hidden variable theories, some physicists explored non-local hidden variable models. Among them was David Bohm, who had earlier proposed a deterministic version of quantum theory in which particles were guided by a hidden wave. Bell himself found Bohm's ideas intriguing, even if they did not restore locality. The debate did not end with Bell's theorem, but it shifted the ground beneath it. The shattering of certainty that Bell's work brought was not limited to physics. Philosophers, mathematicians, and even artists drew inspiration from the realization that reality might be fundamentally interconnected or indeterminate. The classical vision of the world as a machine, ticking forward according to fixed laws, gave way to something more mysterious, something that demanded new ways of thinking about causality, time, and knowledge itself. For Einstein, who had passed away before Bell's theorem was derived, the results would have been devastating. His insistence that the universe must obey local realism had been proven untenable. The dream of hidden variables restoring order had been shattered by mathematics and experiment. Yet in another sense, Einstein's resistance had played a crucial role. By refusing to accept quantum mechanics at face value, he had pushed the field to refine its concepts, to ask deeper questions, and to confront paradoxes that might otherwise have been ignored. Without his challenge, Bell's breakthrough might never have happened. The legacy of Bell's theorem is a paradox of its own. It destroyed the very principles Einstein cherished most, yet it also fulfilled his demand that physics should not rest on philosophy alone. It showed that even the strangest ideas must answer to experiment, and that no matter how unsettling the truth, it is nature that has the final say. Few experiments in the history of science capture the essence of quantum strangeness as powerfully as the double-slit experiment. First performed in the early 1800s by Thomas Young, it was originally intended to settle a simple debate about the nature of light. Was light made of particles, as Isaac Newton believed, or waves, as other thinkers suggested? By shining light through two narrow slits and projecting it onto a screen, Young showed that the result was an interference pattern, the hallmark of wave behavior. Where one wave crest met another, the light intensified, and where a crest met a trough, darkness appeared. This elegant display seemed to prove that light was a wave. For over a century, that conclusion held. Light was understood as a wave, propagating through space much like ripples in water. But then came quantum mechanics, and with it, the realization that light could also behave like a particle. Photons, as these particles of light were called, carried discrete packets of energy, capable of knocking electrons free from metal surfaces, or being counted one by one in sensitive detectors. Suddenly, the picture of light as a simple wave collapsed. It was both wave and particle, depending on how one looked at it. The double-slit experiment took on new significance under this revelation. When physicists repeated it with single photons, sending them through the slits one at a time, they expected to see two clear bands on the screen, corresponding to particles passing through one slit or the other. Instead, over time, an interference pattern emerged, just as if each photon had traveled through both slits at once and interfered with itself. The implication was astonishing. A single particle behaved like a wave, spreading out and exploring multiple possibilities simultaneously. The mystery deepened when scientists attempted to measure which slit the photon actually passed through. By placing detectors at the slits, they forced the photon to reveal its path. The result was immediate and dramatic. The interference pattern vanished, replaced by two distinct bands, just as classical particles would produce. The very act of observation seemed to collapse the wave of possibilities into a single outcome. It was as though the photon adjusted its behavior depending on whether it was being watched. This baffling result lies at the heart of quantum mechanics. The double-slit experiment demonstrates that particles do not have definite paths until measured. Instead, they exist in a superposition of possibilities, described by a wave function that only resolves into certainty when observed. The question of what constitutes an observation, whether it requires a conscious observer or merely an interaction with the environment, remains one of the most debated aspects of physics. Einstein, who had already raised concerns about the role of chance and measurement in quantum mechanics, was particularly unsettled by this implication. To him, the idea that reality depended on observation seemed absurd. Objects, he insisted, must exist in definite states regardless of whether anyone is looking. The double-slit experiment appeared to suggest otherwise, reinforcing the Copenhagen interpretation championed by Bohr and his colleagues. The paradox did not stop with photons. Physicists later repeated the experiment with electrons, atoms, and even molecules consisting of hundreds of particles. In each case, the interference pattern appeared when no measurement was made of the path, and it vanished when the path was observed. This suggested that wave-particle duality was not limited to light, but applied to all matter. At the most fundamental level, everything in the universe seemed to follow the same bewildering rules. What the double-slit experiment reveals is that the boundary between waves and particles, possibility and actuality, is not clear-cut. Quantum objects can behave like waves until forced to behave like particles. The mechanism of this transformation, the so-called collapse of the wave function, remains one of the deepest mysteries in physics. Is it a real physical process, triggered by measurement, or merely a reflection of how knowledge changes when information is gained? Different interpretations of quantum mechanics answer this question in different ways, but none provide a universally accepted solution. Some interpretations, like the many worlds hypothesis, suggest that the wave function never collapses at all. Instead, every possible outcome occurs, but in separate, branching universes. Under this view, the photon passes through both slits, but each outcome exists in a different reality. Others, like Bohm's hidden variable theory, propose that the wave guides the particle, even if the underlying mechanism remains hidden from direct observation. Each approach tries to make sense of the double-slit experiment, but none eliminate its fundamental strangeness. The experiment also forces reconsideration of what it means to measure. When a detector records which slit a photon passes through, the interference disappears. But if the information is recorded and then erased before anyone looks at it, the interference pattern can reappear. This suggests that it is not observation by a human mind that matters, but the availability of information. The photon's behavior depends not only on the present, but also on whether knowledge of its path could exist. The implications of this are staggering. If the double-slit experiment shows that particles behave differently depending on information, then reality itself may be tied to knowledge. The line between what is real and what is known becomes blurred. It suggests a universe where information is as fundamental as matter or energy, where the act of asking a question shapes the answer. The experiment continues to be performed with increasing precision, using new technologies that push the limits of measurement. Each iteration confirms the same bizarre result. Particles behave like waves when unobserved, and like particles when observed. No matter how carefully the conditions are controlled, the mystery remains intact. It is as if nature is reminding us that reality is not what common sense suggests, but something deeper, stranger, and far more interconnected. For physicists, the double-slit experiment is more than a puzzle. It is a window into the heart of quantum mechanics. It encapsulates the paradoxes of superposition, observation, and wave-particle duality in a single elegant demonstration. It challenges the boundaries between physics and philosophy, forcing us to reconsider the role of the observer and the meaning of reality itself. Einstein may never have accepted the implications of the experiment, but he recognized its importance. The double-slit mystery was not an odd quirk to be ignored, but a profound clue to the nature of the universe. In its strange patterns of light and shadow, it revealed a cosmos where possibility and actuality intertwine, where certainty dissolves into probability, and where the act of observing is inseparable from the fabric of existence. Among Einstein's greatest achievements was his radical reshaping of how humanity understood time and space. In his theory of special relativity, time was not a universal ticking clock, the same everywhere for everyone, but something woven together with space into a single fabric. Observers in different states of motion experienced time differently. A fast-moving clock ran slow compared to one at rest, and events that seemed simultaneous to one observer could appear staggered to another. With general relativity, Einstein extended this idea further, showing that gravity itself curved space and bent time. The universe was not a static stage, but a dynamic arena in which time and space responded to matter and energy. This view was elegant, sweeping, and above all deterministic. In relativity, the trajectory of a planet, the bending of light around a star, or the ticking of a clock near a black hole could be calculated with precision. The equations of relativity described a universe in which cause and effect reigned supreme, where the geometry of space-time governed motion as reliably as the gears of a cosmic machine. Quantum mechanics, however, told a very different story. Instead of a smooth, predictable fabric, it described a jittering, probabilistic world at the smaller scales. Time, in quantum theory, appeared not as a continuous flow, but as something more elusive. The equations that governed subatomic particles treated time as a parameter, an external backdrop against which probabilities unfolded, rather than as a dynamic entity shaped by the presence of matter. This was the root of the clash. Relativity made time a player in the drama of the cosmos, bending and stretching as stars collapsed or galaxies expanded. Quantum mechanics reduced time to a simple coordinate, a stage direction with no role in the unfolding action. The two pictures worked beautifully within their domain's relativity, for the vastness of space, and quantum theory for the minuteness of atoms. But when physicists tried to apply them together, contradictions erupted. Consider black holes. Relativity predicted their existence as regions where gravity became so extreme that not even light could escape. Inside, time itself curved toward a singularity, a point of infinite density. Yet when quantum mechanics was introduced into this setting, it predicted that black holes could slowly evaporate by emitting radiation, a process now known as Hawking radiation. The clash between the two theories here was not just technical, but conceptual. Relativity said nothing escapes a black hole. Quantum theory insisted that energy could leak away. Both could not be right in their purest forms, yet each was supported by powerful reasoning. Time itself became the battlefield. In relativity, time flowed smoothly, dictated by geometry. In quantum mechanics, it was chopped into probabilities, with no clear explanation for how events unfolded from one moment to the next. Efforts to unify the two often found that time behaved inconsistently, refusing to fit into a single coherent picture. At the heart of this was the question, is time fundamental, or is it emergent? Something that arises only when larger systems interact. Einstein resisted the idea that time was uncertain or dependent on observation. He saw time as part of the deep order of the cosmos, a structure to be discovered, not an illusion to be dismissed. Quantum mechanics, however, suggested that the very notion of when an event occurred was slippery. Experiments in quantum entanglement showed that correlations between particles seemed to leap across space instantaneously, ignoring the limitations imposed by relativity. If nothing could travel faster than light, how could two particles separated by vast distances behave as though they shared the same clock? The conflict grew sharper as new theories emerged. Some physicists argued that space and time themselves might not be fundamental at all, but derived from deeper quantum processes. Under this view, space-time was like a fabric woven from threads too fine to see, threads made of quantum information. Relativity described the fabric as a whole, but quantum mechanics described the individual threads, whose vibrations gave rise to the appearance of space and time. This picture was tantalizing but incomplete. It suggested that Einstein's vision of a curved space-time was real, but not ultimate, a large-scale approximation of something more granular. The smooth flow of time we experience could be the emergent outcome of countless quantum interactions, just as the solidity of a table is an emergent property of atoms buzzing in motion. Yet no one had fully explained how to move from one picture to the other, from the seamless equations of relativity to the probabilistic rules of quantum physics. The implications extended beyond theory into the very nature of existence. If relativity's time was an objective dimension, stretching from past to future, quantum mechanics' time was more ambiguous, tied to events that may or may not occur until observed. This raised unsettling questions about free will, causality, and the structure of reality. Was the future predetermined by the geometry of space-time, as relativity implied, or was it open and uncertain, shaped by probabilities, as quantum mechanics suggested? Einstein struggled with this contradiction throughout his life. He admired the success of quantum mechanics, but rejected its philosophical core. The randomness of quantum events seemed incompatible with the orderly progression of time in relativity. For him, the two pictures could not remain in tension forever. They would have to be unified into a single framework that preserved causality, determinism, and the coherence of nature. Yet despite decades of work, that unification remained out of reach. Even today, the clash between relativity and quantum mechanics stands as one of the greatest challenges in physics. Attempts at reconciliation through theories such as string theory, loop quantum gravity, and holography continue to wrestle with the role of time. Some suggest that time may be an illusion, a convenient parameter that emerges from deeper, timeless laws. Others argue that time must be fundamental, as Einstein believed, woven into the very structure of reality. What is clear is that both relativity and quantum mechanics cannot be entirely correct in isolation. They are two partial views of a deeper truth, glimpses of a reality that has yet to be fully uncovered. Their clash over time and space is not a sign of failure, but a clue, pointing toward a synthesis that may one day reveal the true nature of the cosmos. Until then, time remains both familiar and mysterious, measured by our clocks and calendars, yet defying our deepest attempts to define it. The most radical leap in 20th century physics came with the recognition that particles were not the ultimate building blocks of reality. Instead, everything arose from deeper entities called fields. These fields extended everywhere, filling the universe completely, and what we thought of as particles were simply excitations, localized ripples, or vibrations in those fields. A photon was not a standalone bead of light energy, but a ripple in the electromagnetic field. An electron was not an isolated speck, but a disturbance in its own field that spanned the cosmos. This framework became known as quantum field theory. It was not a mere add-on to quantum mechanics, but a sweeping generalization, one that provided the mathematical language to describe how particles were born, interacted, and annihilated. For the first time, physicists had a tool that combined the probabilistic character of quantum mechanics with the continuous spread of fields. The results were astonishing. Predictions made by quantum electrodynamics, a branch of quantum field theory, were confirmed with an accuracy unmatched by any other scientific theory. For Einstein, however, this approach stretched beyond what he was willing to accept. He could appreciate the elegance of field concepts, as his own general relativity was built on a field description of gravity, but the quantum version contained something that troubled him deeply: the unavoidable randomness at its core. In relativity, a field curved space in a precise, calculable way. In quantum theory, a field seethed with uncertainty, giving rise to events that no equation could pin down exactly. The vacuum, which classical physics considered truly empty, was redefined. In quantum field theory, emptiness did not exist. What seemed like a void was actually a seething ocean of fluctuating energy, with particles momentarily appearing and disappearing like sparks in darkness. These fluctuations were not just theoretical curiosities. They had measurable consequences. The Casimir effect, in which two uncharged plates in a vacuum were drawn together, revealed that even the emptiest space contained invisible forces at work. Such ideas turned the very concept of nothing inside out. Instead of a passive background, the vacuum was active, shaping the behavior of matter and energy. Space itself was dynamic, humming with potential. To Einstein, this picture was unsettling. He preferred a universe with clear rules and stable structures, not one where emptiness itself behaved unpredictably. Yet experiments consistently reinforced the quantum description. Quantum field theory also introduced the notion that forces were mediated by particles. The electromagnetic force was carried by photons, the weak force by W and Z bosons, the strong force by gluons. These mediator particles were not merely conveniences, but real participants in the fabric of nature. The interactions that governed atoms and nuclei emerged from exchanges of these quanta, weaving together the tapestry of physical reality. What made the framework even more extraordinary was its universality. Once the mathematics was established, it seemed to apply everywhere. The fields were not local patches, but extended across the entire cosmos. Every electron in the universe was a ripple in the same underlying field. Every photon was a vibration of the same electromagnetic sea. This meant that the building blocks of matter were not individual entities, but manifestations of a universal substrate. Despite its power, quantum field theory was not a theory Einstein ever embraced. He admired the precision of its predictions, but distrusted its foundations. For him, the idea that particles popped in and out of existence without cause was an affront to reason. He sought a deeper, more deterministic layer beneath the fields, one that would restore order to the apparent chaos. But as the decades passed, it became clear that the probabilistic framework was here to stay. The reach of quantum field theory extended into realms Einstein never lived to see. It formed the basis of the standard model of particle physics, unifying electromagnetism with the weak and strong nuclear forces. It provided the framework to predict the Higgs boson, a particle discovered in 2012 that confirmed the mechanism by which other particles acquire mass. These triumphs demonstrated that the field concept was not a temporary fix, but a cornerstone of modern physics. Yet even with its success, mysteries remained. Gravity resisted integration into the quantum field framework. While the electromagnetic, weak, and strong forces could be described by fields, Attempts to quantize gravity produced infinities and contradictions. The dream of a fully unified theory, the kind Einstein had sought all his life, remained elusive. The clash between relativity and quantum field theory persisted, reminding scientists that the story was not yet complete. What quantum field theory accomplished, however, was nothing less than a redefinition of existence itself. The solid world of objects and particles gave way to a universe of fields and vibrations, where matter and energy were not separate entities, but different modes of the same underlying reality. The universe was less like a collection of things and more like a grand symphony, with particles as fleeting notes emerging from the continuous music of fields. This vision was at once humbling and empowering. It showed that beneath the appearances of solidity and permanence, everything was fluid, interconnected, and dynamic. It suggested that reality was not built from bricks but from patterns, not from things but from relationships. While Einstein resisted the randomness of this view, he inadvertently paved the way for it by introducing the very idea of fields as the language of nature. Quantum physics simply carried that idea into domains he could never quite accept. The consequences of this shift continue to ripple outward, shaping how scientists think about the cosmos and humanity's place within it. The fields that sustain reality are not confined to laboratories or equations. They are the hidden architecture of the universe itself. Every atom in our bodies, every photon of starlight, every particle of matter is part of this all-encompassing web. To understand quantum fields is to glimpse the underlying unity of existence, a unity that Einstein sought, but could not reconcile with his vision of determinism. For centuries, philosophers and scientists imagined the vacuum as the ultimate symbol of emptiness. It was conceived as a stage where objects moved and forces acted, but the stage itself remained silent, inert, and featureless. Classical physics treated this emptiness as an absence, a pure void stripped of all matter and energy. Einstein himself carried this classical intuition even while reshaping physics with relativity. To him, space was dynamic, capable of curving under the influence of mass and energy, but the vacuum was still empty at its core. What quantum theory revealed, however, was that this intuition was deeply misleading. The quantum vacuum is not a hollow void. Instead, it is a restless medium alive with constant fluctuations. Particles and antiparticles appear spontaneously, borrow energy from the vacuum itself, and then annihilate in fleeting instants. These ephemeral events cannot be directly observed in the way we see electrons or photons, but their effects are undeniable. The vacuum, far from being nothing, is an active and essential component of reality. One striking demonstration of this restless emptiness is the Casimir effect. When two conducting plates are placed very close together in a vacuum, they attract each other without any classical explanation. The phenomenon arises because the space between the plates restricts the kinds of vacuum fluctuations that can exist there, while the surrounding space teems with unrestricted fluctuations. The imbalance produces a measurable force. This simple experiment reveals the astonishing truth. Even in the deepest emptiness, invisible energy is at work. The implications of this insight reach into the fabric of the cosmos. If the vacuum is full of fluctuating energy, then empty space itself contains an immense reservoir of power. Physicists call this zero-point energy, and calculations suggest it is unimaginably large. Every point in space, no matter how remote, is alive with it. Yet, despite its magnitude, this energy usually cancels out when viewed from a macroscopic scale. It lurks in the background, influencing events subtly rather than overwhelming them. For Einstein, such a picture would have been profoundly unsettling. He sought an ordered cosmos governed by deterministic laws, not one where particles blinked into existence unpredictably. In his view, if the vacuum was filled with energy, that energy should be described by clear equations and physical structures. not by probabilistic foam. But quantum field theory demonstrated that the foam-like vacuum was not a philosophical invention. It was a necessity. Without these fluctuations, many observed phenomena would remain inexplicable. One of the most dramatic consequences of the quantum vacuum appears in cosmology. Observations show that the universe is expanding at an accelerating rate, as though space itself were pushing outward. The most plausible explanation is a mysterious energy pervading space, dark energy. While its exact nature remains unknown, one candidate is the energy of the vacuum itself. If true, then the restless fluctuations of nothingness are driving the evolution of the cosmos on the largest scales. The quantum vacuum also plays a role near black holes. According to Stephen Hawking, pairs of virtual particles that arise in the vacuum near the event horizon can be separated, with one particle falling into the black hole while the other escapes. The escaping particle becomes real, leading to what is now called Hawking radiation. Over immense timescales, this process causes black holes to lose mass and eventually evaporate. A phenomenon as monumental as the death of a black hole may ultimately trace back to the quantum jitter of emptiness. Even in particle physics, the vacuum is far from neutral. The Higgs field, a kind of vacuum field, permeates space and gives mass to particles. Without it, electrons and quarks would be weightless, unable to form atoms or matter as we know it. The discovery of the Higgs boson in 2012 confirmed that the vacuum is not passive. It shapes the very structure of existence. Empty space is a foundation, a matrix that imparts properties to everything within it. What makes the quantum vacuum particularly remarkable is its paradoxical character. On one hand, it embodies absence, no ordinary particles, no radiation, no visible matter. On the other hand, it is an ocean of hidden activity, overflowing with energy and potential. This duality challenges our most basic intuitions about reality. It forces us to accept that nothing is not truly nothing, but a seething background upon which the drama of the universe unfolds. Einstein might have resisted this interpretation, clinging to a vision of a calmer cosmos. Yet the evidence is relentless. From the Casimir effect to Hawking radiation, from the Higgs field to dark energy, the vacuum reveals itself as an indispensable player in physics. It does not sit idly by. It shapes forces, structures, and the destiny of the universe itself. The realization that empty space is alive with hidden energy is one of the most profound revelations in science. It transforms our perception of reality. Where once we saw void, we now see possibility. The vacuum is not the absence of being. It is the ground of being, the hidden reservoir from which the universe draws its shape and power. The most persistent fracture line in modern physics lies between the smooth geometry of Einstein's relativity and the jittering uncertainty of quantum mechanics. Each framework is extraordinarily successful within its domain. Relativity describes the vast cosmic scale with unmatched accuracy, explaining how mass curves space, how black holes bend time, and how the universe expands. Quantum mechanics reigns supreme in the microscopic realm, accounting for the strange behavior of electrons, photons, and fields. But the two theories, despite their triumphs, speak entirely different mathematical languages. Where one paints reality as continuous and deterministic, the other insists on discreteness and probability. The unresolved task of reconciling these pictures is the problem of quantum gravity. Einstein himself devoted the later decades of his life to the pursuit of unity. He was convinced that the laws of nature must be woven together by a single coherent principle. His hope was that gravity and electromagnetism could be integrated, forming a unified field theory. While he worked tirelessly, the quantum revolution surged ahead in directions that did not align with his vision. By the time he passed away, the split between relativity and quantum mechanics was sharper than ever, and the problem he had set his sights on remained unsolved. At its core, the tension arises because relativity treats space-time as a smooth fabric that can bend but never breaks. Quantum mechanics, on the other hand, reveals that all fields, particles, and forces are quantized into discrete packets of energy. If space-time is itself a field, then it too must have a quantum structure. This suggests that gravity, which emerges from space-time curvature, should also exist in quantized units gravitons. Yet no experiment has ever detected such particles. The challenge becomes especially urgent in extreme environments, near the singularity of a black hole. The equations of relativity predict infinite density, a breakdown of the very laws of physics. In the earliest instance of the Big Bang, space-time was compressed into an unimaginably small scale, where quantum effects cannot be ignored. These conditions demand a theory that merges relativity with quantum principles, but each attempt so far has been partial, incomplete, or speculative. One of the most ambitious approaches is string theory. Instead of treating particles as points, it proposes that the fundamental constituents of reality are tiny vibrating strings. Different vibrations give rise to different particles, and the framework naturally includes a quantum version of gravity. But string theory requires additional spatial dimensions beyond the familiar three, and so far, its predictions remain untested. It offers elegance and mathematical beauty, but its experimental verification continues to elude scientists. Loop quantum gravity presents a different strategy. Rather than introducing strings or extra dimensions, it suggests that space-time itself is granular at the smallest scale. It is built of discrete loops woven into a vast network. These loops create the geometry of space, giving rise to area and volume in quantized chunks. If this picture is correct, then the fabric of the cosmos is not continuous at all, but pixelated at the Planck scale. While promising, this idea is still incomplete, and many questions remain about how it connects with the macroscopic world. The search for quantum gravity is not just about technical unification. It also forces us to rethink what reality is. If space-time is quantized, then the very notion of smooth, flowing time may be an illusion that emerges only at large scales. If gravity can be expressed in quantum terms, then black holes and the Big Bang must be reinterpreted in ways that avoid singularities. These are not abstract problems confined to chalkboards. They are fundamental to our understanding of origins, destiny, and existence. Einstein's dream of unity echoes in every attempt to bridge the divide. He believed that the cosmos could not be built on two conflicting foundations. His pursuit, though incomplete, set the stage for generations of physicists who refused to accept the fracture between relativity and quantum mechanics as permanent. The absence of a solution is itself a mystery, a challenge left by the universe as though daring us to discover the missing piece. The problem of quantum gravity remains one of the greatest frontiers in science. Experiments probing black holes, gravitational waves, and the earliest moments of the universe may someday provide clues. Whether the answer lies in strings, loops, or an entirely new paradigm, the reconciliation of these two great pillars of physics will reshape our conception of reality. Until then, we live in a world where space-time bends smoothly in one framework and quivers probabilistically in another, a contradiction that even Einstein could not resolve. Few concepts stretch the imagination as far as the possibility of the multiverse. For much of scientific history, the universe was thought to be singular, complete, and absolute. The cosmos was everything there was, and everything there would ever be. Yet quantum theory, with its insistence on superpositions and probabilities, opened a door to an unsettling possibility. Perhaps our universe is not the only one. Perhaps reality itself is only one branch among countless others, endlessly branching and existing in parallel. The seeds of this idea can be traced to the quantum principle of superposition. At the microscopic level, particles can exist in multiple states at once. An electron can be here and there simultaneously, A photon can travel along two paths at once, and only when measured does the system resolve into a definite outcome. But what does it mean for a particle to choose one path? If superposition is real, perhaps the other possibilities do not vanish. Perhaps they continue, unfolding in parallel, each as real as the outcome we observe. This line of thought was developed into the many worlds interpretation by Hugh Everett in the mid-20th century. In his view, every quantum measurement splits reality into multiple branches. Each possible outcome becomes actual, not just in theory, but in existence. When you observe a quantum event, you do not eliminate possibilities. You divide into versions of yourself, each inhabiting a different world. The universes multiply endlessly, with each branch containing its own version of events. To many, this interpretation sounds extravagant, even absurd, yet it resolves one of the most puzzling aspects of quantum mechanics, the measurement problem. Instead of requiring a collapse of the wave function, which has no clear physical mechanism, the many worlds view accepts the mathematics literally. The wave function evolves smoothly according to quantum laws, and every outcome is realized. The price is that reality is not singular, but a vast tree of branching universes. The implications are staggering. If the multiverse exists, then every choice, every roll of the dice, every quantum fluctuation generates a divergence. In one branch, a particle passes through the left slit. In another, through the right. In one world, you decided to read these words. In another, you did not. Some branches might differ only by the tiniest detail, while others may diverge so radically that they form entirely different histories, even different laws of physics. Cosmology adds further weight to the idea. The theory of cosmic inflation, which describes the rapid expansion of space in the earliest moments of the universe, suggests that inflation may never completely end. Instead, it produces endless bubble universes, each with its own properties. Our universe could be just one bubble in an infinite cosmic froth, each pocket with its own constants, forces, and possibilities. If so, then the multiverse is not just a quantum speculation, but a cosmological inevitability. Critics argue that the multiverse may be untestable, a hypothesis beyond the reach of science. If we can never interact with other universes, how can we know they exist? Yet defenders respond that the multiverse may explain puzzles that single universe models cannot. Why are the constants of physics so finely tuned for life? In a multiverse, countless combinations exist, and we happen to inhabit one where the values allow complexity and consciousness. What seems miraculous becomes inevitable in a landscape of infinite variation. Einstein himself never entertained such radical plurality. His vision of the cosmos was unified and singular, an ordered whole guided by rational laws. The idea that reality might fracture into countless versions would have clashed with his sense of harmony. Yet the quantum world continues to challenge the very assumptions he held most deeply. The multiverse, whether real or not, emerges naturally from the mathematics of quantum mechanics, and it refuses to be dismissed. To imagine the multiverse is to stretch human imagination to its limit. It forces us to accept that what we see and know may be only a sliver of what truly exists. Our universe, vast and ancient as it is, could be nothing more than one thread in a boundless tapestry. Each branch, each bubble, each parallel world is as real as our own, even if forever beyond our reach. The mystery is not just whether these universes exist, but what it means for us if they do. Among the strangest frontiers opened by quantum mechanics lies the question of consciousness. Unlike equations about particles or fields, this subject touches directly on the mystery of our own existence. The puzzle is not just how matter behaves, but how awareness itself arises. Some have proposed that the key to understanding the mind may lie hidden within the principles of quantum theory. Others insist this speculation is misguided, a leap too far. Yet the idea continues to haunt scientific debate. The starting point is the measurement problem. In quantum mechanics, systems evolve as probabilities until they are observed. An electron remains in superposition until its position is measured. A photon travels in many paths until detection. The collapse of the wave function seems tied to observation, and this raises an uncomfortable question. What role does the observer play? Does consciousness itself cause the collapse? Or is the collapse simply a physical process independent of awareness? This line of thought attracted thinkers who believed the mind might be inseparably linked with quantum processes. The mathematician John von Neumann argued that the chain of measurement cannot be completed without invoking the conscious observer. Later, physicist Eugene Wigner considered the possibility that consciousness was fundamental to the act of observation. For them, the quantum world suggested that mind could not be separated from matter, that the act of knowing was part of the fabric of physical reality. Einstein rejected such notions outright. For him, consciousness was not a scientific problem, but a biological one, something to be explained by neurobiology rather than by quantum theory. He was deeply uncomfortable with interpretations that gave the human mind a privileged role in the structure of reality. To Einstein, that was too close to mysticism. He believed that physics should describe the external world, not collapse into metaphysics. Yet modern science has not entirely dismissed the possibility. Some researchers suggest that the brain, with its enormous complexity and sensitivity, could exploit quantum effects. The physicist Roger Penrose, together with anesthesiologist Stuart Hameroff, developed the Org-OR hypothesis, proposing that consciousness arises from quantum processes within microtubules in neurons. In this view, awareness is not just an emergent property of neural connections, but a direct consequence of quantum activity. The idea remains controversial. Critics argue that the brain is too warm and noisy for fragile quantum states to survive. Decoherence should erase superpositions long before they could play a role in thought. Traditional neuroscience explains consciousness in terms of information processing, networks of neurons firing in patterns that give rise to experience. For many, quantum explanations seem unnecessary when classical mechanisms suffice. Still, the possibility continues to intrigue because it addresses puzzles that classical models cannot. Consciousness is not just information processing. It is subjective experience, the what it feels like to be aware. This inner perspective, known as the hard problem of consciousness, remains unsolved. Some wonder whether quantum mechanics, with its intrinsic indeterminacy and non-local connections, might offer clues where classical physics falls silent. Beyond neuroscience, the link between quantum theory and consciousness sparks philosophical reflection. If observation plays a role in determining outcomes, then awareness may not simply be a byproduct of physical processes, but a participant in them. The boundary between the observer and the observed becomes blurred. Reality, in this picture, is not independent of mind but intertwined with it. Whether this is literal truth or poetic metaphor remains contested. Einstein's caution seems justified here. He resisted dragging consciousness into quantum debates, fearing it would obscure rather than clarify the science. He preferred to believe that physical reality exists regardless of whether anyone observes it. His dream was a universe governed by objective laws, not shaped by subjective minds. Yet the enduring fascination with the quantum mind shows that the questions he avoided have not disappeared. The connection between quantum mechanics and consciousness remains speculative, but it forces us to confront mysteries that neither physics nor philosophy has fully resolved. Are we merely complex arrangements of matter obeying physical laws, or do we play a deeper role in shaping the reality we experience? The answer may never satisfy both scientists and philosophers, but the very act of asking shows how quantum theory pushes us beyond equations into questions about existence itself. The flow of time feels obvious to us. We remember yesterday but not tomorrow. We see glasses shatter but never spontaneously reassemble. and we grow older rather than younger. This one-way direction is so ingrained in our lives that we rarely question it. Yet when physicists examine the equations of quantum mechanics, they find no built-in distinction between past and future. The mathematics works equally well forwards or backwards. Time's arrow, the thing we take as natural, appears instead to be an illusion arising from deeper principles. One way to understand this puzzle is through entropy, the measure of disorder. In classical thermodynamics, entropy always increases, giving time its forward push. A hot cup of tea cools, but a cold cup never heats itself without input. This irreversible trend defines the arrow of time in everyday experience. But quantum mechanics complicates the picture. At the smallest scales, particles interact in ways that are reversible. A collision between two electrons can be mathematically run backwards with no contradiction. So where does the sense of direction come from if the foundations do not demand it? Some researchers argue that the arrow of time is not a fundamental feature of nature, but emerges from the quantum process of measurement. When a superposition collapses, possibilities condense into one outcome. The past becomes fixed while the future remains open. This collapse gives a sense of direction, from uncertainty to certainty, from potential to actuality. In this view, time's flow is tied to the way information solidifies in the quantum world. Others see entanglement as the key. When systems interact, they become correlated, and information spreads outward irreversibly. A particle entangled with its environment cannot be disentangled without extraordinary precision. This spreading of information creates what appears to us as irreversibility, and with it, a forward-moving arrow. The universe, through entanglement, builds a record of itself that cannot be undone. Still more radical proposals suggest that time itself may not be fundamental at all. In certain formulations of quantum gravity, the equations describing the universe contain no explicit time variable. Instead, time emerges as a relational property between events, not as a backdrop against which they unfold. If this is true, then the arrow of time is not written into the structure of reality, but arises from the way we perceive and interact with it. Einstein, with his theory of relativity, already challenged the idea of universal time. For him, time was woven together with space into a four-dimensional continuum. Different observers could disagree on the order of events depending on their motion, yet relativity still preserved causality. Effects followed causes. Quantum mechanics further unsettles this order by allowing correlations that seem to transcend classical cause and effect. Some experiments even suggest that choices made in the present can influence the state of a particle in the past, a phenomenon known as retrocausality. If quantum mechanics permits such behavior, then the flow of time may be less rigid than we assume. The arrow could bend, reverse, or dissolve under certain conditions. For most of us, such possibilities remain invisible because the macroscopic world smooths over quantum strangeness. But at the smallest scales, the rules may allow a reality where past and future intertwine. The implications reach beyond physics into philosophy. If time's direction is emergent rather than fundamental, then our experience of it is not a reflection of universal law, but of human perspective. Memory, anticipation, cause and effect, these could be properties of how consciousness interprets quantum processes rather than features of the cosmos itself. What we call the present may be the point where possibilities collapse, leaving behind a trail we label the past and opening paths we call the future. Einstein never accepted such fluidity. For him, the passage of time was a stubborn illusion, a trick played by our senses. He believed the universe existed as a complete four-dimensional block, with past, present, and future equally real. Quantum mechanics, however, leaves open the possibility that the arrow of time is less about illusion and more about the quantum act of becoming, the constant crystallization of potential into reality. The quantum arrow of time remains one of the most profound mysteries It forces us to question not only the mechanics of the universe, but the nature of our own existence within it. Is time a fundamental river carrying us along, or a pattern stitched together by measurement, entropy, and perception? Whatever the answer, it shows that what feels most solid and obvious, the flow from yesterday to today to tomorrow, may be as elusive as the particles dancing in the quantum realm. Throughout history, humanity has wondered whether the world we perceive is the ultimate reality or a veil concealing something deeper. In modern times, this ancient philosophical curiosity has taken a new form. The simulation hypothesis. The idea suggests that our universe may not be a physical construct at its foundation, but the output of an unimaginably advanced computational system. Quantum mechanics, with its baffling uncertainties and peculiar rules, often serves as the strongest evidence for this possibility. What makes quantum mechanics so provocative in this context is its tendency to behave like information rather than substance. When particles exist in superposition, they hold multiple potential states simultaneously, only collapsing into a single outcome when measured. This has led some thinkers to propose that reality functions like a program that renders detail only when observed, similar to how video games display graphics only where the player is looking. If the universe behaves this way, then perhaps it operates on rules not unlike lines of code. Consider the pixel-like nature of existence. Quantum theory suggests there may be fundamental limits to divisibility's smallest measurable units of energy, length, or time. Space and energy might not be infinitely continuous, but instead granular, much like pixels on a screen or bits in a computer. If true, this granularity hints that the fabric of the universe could resemble a digital structure rather than an analog one. Instead of infinite smoothness, everything could be composed of indivisible packets of information. Another intriguing feature is entanglement, where particles influence each other instantaneously across distance. From the perspective of a simulation, entanglement may be akin to variables in a program linked by shared code. No signal needs to travel between them, because their outcomes are governed by the same underlying instructions. What feels spooky to physicists could be natural in a computational framework, where global rules define local realities. The double-slit experiment, one of the most iconic demonstrations in physics, also fits neatly into this analogy. Particles behave like waves of probability until an observation forces them into definite paths. This looks eerily like conditional rendering information existing as probability, until the system requires a concrete value. In other words, the universe may not waste resources computing all possible outcomes, but instead resolves them at the moment of measurement. Modern technology has fueled these interpretations. As virtual reality advances, humans have become capable of creating immersive simulated environments where digital beings could, in theory, question the nature of their own existence. If we can simulate rudimentary realities today, some argue, then a civilization far older and more advanced might easily simulate entire universes indistinguishable from real ones. In that light, the probability that our universe is simulated may be higher than the chance it is the original base reality. However, the hypothesis is not merely a thought experiment. It raises testable questions. For instance, if the universe is a simulation, then there might be detectable limitations, like maximum resolutions or quantization of space-time, that betray its computational origin. Some scientists have even proposed experiments to search for such signatures, like anomalies in cosmic rays or unexpected patterns in the cosmic microwave background. Critics counter that the simulation idea is unfalsifiable. If we are inside a perfectly designed system, how could we ever hope to prove it? Any evidence we discover could itself be part of the programming. For Einstein, such speculation would likely have been unappealing, as it replaces the pursuit of physical law with metaphysical storytelling. Yet the peculiarities of quantum mechanics refuse to silence the question. The fact that reality seems dependent on observation, that probabilities collapse into facts, continues to spark debate over whether existence behaves more like computation than material. The philosophical implications are staggering. If we inhabit a simulation, then our notions of free will, purpose, and reality itself shift. Are we simply characters within a cosmic experiment? Is the simulation designed for observation, entertainment, or some purpose beyond comprehension? Or is the very question a misinterpretation, a projection of human technological metaphors onto mysteries that demand deeper understanding? Regardless of whether the hypothesis holds truth, its intersection with quantum mechanics has reinvigorated old debates about the nature of existence. Rather than treating physics as a search for mere particles and forces, the simulation question reframes it as a quest to uncover whether the universe itself is an expression of information. That idea, radical though it sounds, fits comfortably within the quantum world, where information often appears more fundamental than matter. Einstein resisted mysticism, preferring to ground physics in determinism and clarity. Yet even he might have marveled at the way quantum mechanics seems to open the door to realities where information, not substance, is the foundation. Whether the universe is computed or simply behaves in ways reminiscent of computation, the simulation hypothesis underscores how quantum mechanics challenges the boundary between physics and philosophy. In contemplating this possibility, we confront the deepest of questions. Not just how the universe works, but whether it is even what it seems. Quantum mechanics provides the evidence, but it is our imagination that dares to ask whether behind the equations lies not only mystery but design. The puzzles that unsettled Einstein more than a century ago remain alive today, not as relics of history, but as active frontiers that shape the most ambitious scientific projects of our time. What began as theoretical debates about uncertainty, entanglement, and observation has evolved into technologies, experiments, and philosophies that continue to stretch the boundaries of human knowledge. Far from being settled, quantum mechanics is still a source of both confusion and inspiration, and the questions Einstein raised now guide entire fields of research. One of the clearest frontiers is quantum computing. Unlike classical computers, which process information in binary units of zeros and ones, quantum computers rely on qubits quantum states that can exist in multiple superpositions at once. This gives them the potential to solve problems that would take classical machines longer than the age of the universe. Algorithms designed for quantum processors can optimize complex systems, break encryption, and simulate molecular interactions at a level of precision no current technology can approach. Yet even here, the ghost of Einstein lingers. If the universe itself resists determinism, how does a machine built on those principles guarantee stable results? Researchers continue to wrestle with quantum error correction, decoherence, and the strange reality that their most powerful tool is itself unpredictable. Parallel to quantum computing is the pursuit of quantum communication. Entanglement, once derided as spooky action at a distance, is now the foundation for secure information transfer. By linking particles across vast distances, scientists are working to build unhackable networks where eavesdropping becomes physically impossible. Early demonstrations have already transmitted entangled photons between satellites and Earth, suggesting the dawn of a quantum internet. This technology, while still in its infancy, could transform global communication, cryptography, and even diplomacy. Yet its development raises profound questions. If information can leap across space without a visible carrier, what does that imply about the underlying structure of reality? Beyond applications, physicists are pressing into questions that haunted Einstein, but have grown even sharper with time. The problem of quantum gravity remains unsolved. String theory, loop quantum gravity, and other frameworks compete to merge relativity with quantum mechanics. each proposing radically different visions of the universe's architecture. While experiments at particle accelerators or cosmological observations provide hints, no consensus has yet emerged. Some approaches suggest that spacetime itself is emergent, a secondary feature arising from deeper informational processes. If true, then the very stage on which physics unfolds may not be fundamental at all, but the result of underlying quantum interactions. Cosmology has also entered the quantum arena. The inflationary model of the early universe, supported by observations of cosmic background radiation, suggests that quantum fluctuations at the birth of time seeded the galaxies we see today. Quantum effects may not only rule the microscopic realm, but also have shaped the grandest structures in the cosmos. This challenges the classical separation between the very small and the very large, an idea Einstein would have resisted, but which modern science increasingly embraces. Another horizon lies in the study of black holes. These cosmic objects force the most direct clash between relativity and quantum theory. Einstein's equations describe their gravitational pull and event horizons, but quantum mechanics insists that information cannot be destroyed. The paradox of what happens to matter and information falling into a black hole continues to confound researchers. Recent breakthroughs, like the holographic principle and the concept that black holes may encode information on their surfaces, suggest that reality may be stranger and more interconnected than even Einstein imagined. Meanwhile, the intersection of quantum mechanics with biology and neuroscience hints at questions Einstein avoided entirely. Some researchers investigate whether quantum effects play roles in photosynthesis, bird navigation, or even the brain itself. While the idea of a quantum basis for consciousness remains controversial, it reflects a willingness to explore mysteries at the edge of credibility. Einstein's instinct was to keep physics separate from such speculation, but the 21st century thrives on these interdisciplinary bridges. Philosophy has not remained untouched. Debates rage over whether quantum mechanics demands a multiverse, whether it implies hidden variables, or whether it simply reflects the limits of human perception. Interpretations proliferate, from the Copenhagen view to many worlds, pilot wave theories, and new frameworks that treat information as the most fundamental reality. Each carries implications for how we understand existence, choice, and meaning. Einstein might have been skeptical, but his insistence on clarity still echoes in the demand that interpretations provide not just mathematics, but a coherent picture of reality. What is striking about today's quantum frontier is not just the complexity of the science, but the ambition of the questions. Researchers are no longer content to describe what happens when particles collide. They seek to uncover why the universe exists at all, whether reality has boundaries, and what laws govern the deepest layers of being. These are not merely technical puzzles, but existential inquiries, echoing the ancient human desire to know whether we live in a cosmos of order or chaos. Einstein's discomfort with quantum mechanics has, paradoxically, become one of its greatest legacies. His challenges forced others to sharpen their experiments, refine their theories, and push into unknown territory. Today, every quantum computer built, every entangled particle measured, and every black hole studied bears traces of his influence. By refusing to accept quantum mechanics as complete, Einstein ensured that future generations would never settle for easy answers. As we look forward, it is clear that the quantum revolution is still in its infancy. Technologies built on its principles could reshape civilization, while theories born from its puzzles may redefine our place in the cosmos. What remains constant is the sense of wonder, the feeling that beneath every solved equation lies another riddle waiting to emerge. Einstein may not have solved the mysteries of quantum mechanics, but he gave us something just as valuable: the drive to keep questioning, to keep probing, and to accept that the universe is far stranger and more profound than we can yet imagine. The journey through the quantum world leaves us with more questions than answers. Einstein's brilliance illuminated paths that no one had walked before. Yet his refusal to accept the strangeness of quantum mechanics also highlights the limits of even the greatest human mind. The paradox is striking. He gave us tools to understand time, gravity, and light with unmatched precision. But when it came to the microscopic fabric of reality, he could not bring himself to fully embrace its indeterminacy. Today, more than a century after the birth of quantum theory, the same puzzles remain unsolved, their outlines sharper and their implications deeper than Einstein could have foreseen. One of the greatest mysteries is the nature of measurement itself. What actually happens when a quantum system collapses into a definite outcome? The mathematics of wave functions works flawlessly to predict probabilities, but it sidesteps the question of how a possibility becomes an actuality. Physicists still debate whether collapse is a fundamental process, a reflection of hidden variables, or simply an illusion created by our limited perspective. Einstein's discomfort with chance was not misplaced. The act of measurement continues to be one of the strangest and most contested frontiers of science. Entanglement remains another unresolved enigma. Experiments have confirmed its reality beyond any doubt, yet the underlying mechanism is still unclear. How do two particles, separated by vast distances, maintain such a perfect connection? The phenomenon challenges our classical assumptions about space, time, and locality. Some interpretations suggest that entanglement points to a deeper level of reality, one where space itself is secondary, emerging from patterns of information. If so, Einstein's sense of incompleteness in quantum mechanics may have been correct, though the truth might lie far outside the frameworks he considered possible. Gravity, too, defies reconciliation with the quantum world. Relativity describes space-time as smooth and continuous, while quantum mechanics insists on discreteness and uncertainty. Unifying the two has eluded even the most brilliant efforts. String theory, with its extra dimensions and vibrating filaments, promises elegance but lacks decisive experimental proof. Loop quantum gravity offers a different vision, where space-time itself is woven from finite loops, but it too remains incomplete. The dream of a single, unified theory of everything, a dream Einstein pursued obsessively, remains just that, a dream suspended between speculation and discovery. Cosmology raises questions that extend these puzzles to the scale of the universe itself. Why did the Big Bang happen at all? What lies beyond our observable horizon? Did quantum fluctuations birth the cosmos? Or are we one of many universes in an endless multiverse? Each possibility carries implications so profound that they border on the philosophical. Einstein sought certainty in the laws of nature, yet the cosmos seems to resist simple closure. As if the deeper we look, the more the answers dissolve into fresh enigmas. Even time itself refuses to yield clarity. On the one hand, relativity treats time as a dimension woven into space. On the other, quantum mechanics offers no universal clock, no agreed-upon flow. Is time fundamental, or is it an emergent property of quantum processes? Some physicists suspect that what we experience as the passage of time is nothing more than an illusion generated by entropy and probability. If true, Einstein's vision of time as flexible yet real may need to be revised once more, this time in ways that overturn our most basic intuitions. At the intersection of physics and philosophy lies the ultimate unsolved question. What is reality? Is the universe fundamentally made of particles, waves, fields, or information? Are the laws of nature eternal truths? Or are they themselves emergent, shifting over cosmic epochs? Quantum mechanics hints that the universe may be less like a machine and more like a vast computation, a system of relationships rather than objects. Such an idea might have frustrated Einstein, who sought clarity, yet it also speaks to the richness of the mystery he never abandoned. Perhaps what remains most striking is that every new answer seems to deepen the mystery rather than resolve it. The quantum revolution has given us unprecedented control over matter and energy, but it has not erased the paradoxes that defined its birth. Instead, it has revealed that reality is layered, complex, and resistant to final definitions. Einstein's insistence that quantum mechanics was incomplete might have been both right and wrong. Right in sensing that something deeper lies beneath, wrong in assuming that nature must conform to human expectations of simplicity. The enduring lesson is that science is not a finished book, but an endless dialogue with the unknown. Einstein's doubts remind us that even the greatest theories are provisional, stepping stones across an infinite sea. The mysteries he left behind are not failures, but invitations, challenges to continue asking, testing, and reimagining. To confront these puzzles is to accept that our understanding is partial, that the universe is larger, stranger, and more profound than any one theory can contain. In the end, what remains unsolved is not just a set of technical problems, but the very question of what it means to know. Einstein's journey through the quantum world was unfinished, but perhaps that is the truest reflection of reality itself. Knowledge is not a final state, but a living process, always evolving, always incomplete. The mysteries that resisted Einstein's mind still stand before us, not as barriers, but as horizons, reminders that the universe has more to say than we have yet learned to hear.